So in infinite dimensions, the weak topology is strictly smaller than the norm topology. We will prove the statement. This is only a claim, okay, claim. Okay. Before that, so we will show examples of sets which are norm closed but which are not weakly closed, which are norm open which are not weakly open. Okay, so then obviously the two things are same. Okay, so proposition. C, a convex and norm closed set in V, of course V is Banach. Then C is weakly closed. So as I said, we will show there exists norm closed sets which are not weakly closed in infinite dimensions. However, convex closed sets are also always weakly closed. So for convex sets, so the example which we will take will be non-convex, obviously. Okay, so let us take C. So proof. So let x naught not belong to C. Then by Hahn-Banach, there exists an F in V star and alpha in R such that f of x naught is strictly less than alpha, strictly less than f of x. In fact, C is a closed convex set, x naught is a compact convex set, so you can strictly separate them, and therefore you have f of x naught less than alpha less than f of x for all x in C. So now you take U, it will set of all x in V such that f of x is strictly less than alpha. Then U is weakly open, x naught belongs to U, and U intersection C is empty. So the complement contains every point, so this means that C complement is weakly open, implies C is weakly closed. Okay. So now we have a definition from topology, you might have already seen it. So X tau is a topological space and F from X to R a given mapping, given function. We say that F is lower semi-continuous if for every alpha in R we have F inverse of minus infinity alpha equals set of all x in X such that Fx is less than or equal to alpha is closed in X. So such a function is called lower semi-continuous. So of course continuous always implies lower semi-continuous. So lower semi-continuous abbreviation is LSC, that is the abbreviation for lower semi-continuous, and therefore any continuous mapping is lower semi-continuous. So if F is lower semi-continuous, then we have, and Xn converges to X in capital X, then f of x is less than or equal to lim inf n tending to infinity f of xn. So this is a useful result to know. Okay, so why is this true? So proof of this statement, alpha equals lim inf f of xn. Then by the definition of lim inf, then for every epsilon positive there exists a subsequence fnk xnk, sorry, such that f of x and k will be less than or equal to alpha plus epsilon. Because what is lim inf? It is a soup of the inf of the f's, f of xn. Soup over all n, inf of m bigger than or equal to n, f of xm. So then if the soup is equal to alpha, then there must be, for alpha less than plus epsilon, the inf must be between alpha and alpha plus epsilon. Okay, so this is what we are saying, and therefore this will be true. Now, but then since xn k converges to x and f is lower semi-continuous, this implies that fx is also less than or equal to alpha plus epsilon. Now epsilon is arbitrary, so this implies fx is less than or equal to alpha, which is the limit. Okay, so this is so now we have a corollary. V Banach and phi from V to R, a convex and V and lower semi-continuous function with respect to norm topology. So it's lower semi-continuous in the norm topology. Then phi is also weakly lower semi-continuous. Weakly lower semi-continuous, that means lower semi-continuous in the weak topology. So in particular, x mapping to norm x, this is a convex and continuous function, therefore it is lower semi-continuous, and therefore it is weakly lower semi-continuous, and of course norm x is less than or equal to lim inf norm xn n tending to infinity if xn converges weakly to x. So this is another proof of the same thing. We already proved this statement, and now you have a second proof of the same statement. Okay, so proof. So you take alpha in R and phi inverse of minus infinity to alpha. So this phi is phi is convex, so this set is convex, and it is also closed since phi is lower semi-continuous, okay, in the norm topology. So convex and closed in the norm topology, and by the previous proposition, this implies this is weakly closed, and therefore phi is weakly lower semi-continuous. Okay. So now some notation. We will take V Banach and then we will say D is set of all x in V such that norm x is strictly less than 1. This is the open unit disk. Okay, so open unit ball. Okay. B is the closed unit ball, so x in V, norm x is less than or equal to 1, closed unit ball. And S is the unit sphere, x in V, such that norm x equal to 1. So unit sphere. Okay. So example, S is closed in norm topology if V is infinite dimensional, S is never weakly closed. So you have a set which is closed in the norm topology, which will never be closed in the weak topology if V is infinite dimensional. So in the infinite dimensional, our claim is established, namely the two topologies are strictly different. Okay. So let us take x naught in V and such that norm x naught equal to 1. So x naught norm x naught is strictly less than 1. So x naught belongs to D. Okay. So now take any neighborhood U of x naught, any weak neighborhood of x naught. So what is it? It is U will be set of all x in V such that mod Fi of x minus x naught is less than epsilon for all 1 less than equal to I less than equal to n. So it's some finite set I am taking. So Fi belong to V star. Okay. So epsilon is positive and so on. Okay. So now you consider the map A from V to Rn. So A of x equals F1. We have done this kind of mapping before, Fx xn. Then A is not injective. Because if A were injective, then you have a 1-1 map from V into Rn. This, because if not, dimension of V will be less than or equal to n, which is a contradiction because V is infinite dimensional. So this is not possible. Okay. So this is not in. So there exists a x there exists a x. So let me call it y naught. Y naught in V such that you have that Fi of y naught equal to 0 for all 1 less than to I less than equal to. Then you take x naught plus ty naught. This belongs to U for all t. Because Fi of y naught is 0, so if I just added it, nothing will change. So if x naught is in U, then you have therefore this also there. Now you look at g of t equals norm of x naught plus ty naught. So this y naught not equal to 0. Okay, because it's not injective, so you have this. Okay, so then g of 0 equals norm x naught, which is strictly less than 1, and g of t tends to, by the triangle inequality, this tends to plus infinity as t tends to plus infinity. So there exists a t naught such that g of t naught equals norm of x naught plus ty naught equal to 1. What does this mean? That is, there exists a point x naught plus t naught y naught belonging to the neighborhood U intersection S. So any neighborhood of x naught will intersect S, and therefore D is contained in the weak closure of S. And S is already there. This means that B is contained in the weak closure of S. But then B is convex and norm closed, implies B is weakly closed. Therefore, B equals weak closure of S. So you have the unit sphere in the weak topology. Its closure is in fact the entire closed ball. Okay, so this is a very strange situation, and therefore you have that S is not weakly closed because its closure is much bigger than it. Okay, so this shows that the two are entirely different. So another example, which is almost the same as the previous one. So V Banach, then D is not weakly open. So you know, in the norm topology, the ball is the fundamental thing. So if here you are saying the open unit ball, which is a norm open set, that's the basic kind of open set, the ball, this is not weakly open. Why is it not weakly open? So if you took x naught in D, then you have any neighborhood U, any weak neighborhood of x naught contains the affine subspace x naught plus ty. So it contains the whole line. Okay, it contains the whole line passing through x naught, and therefore it's a very big set. So open neighborhoods are very large, and therefore it does not contain, and therefore U is not contained in D. So D cannot contain any weak neighborhood, and therefore D is not weakly open.